To create any of these effects, all you need is a text editor and JavaScript. It might be easier than you think. The most important HTML canvas method that allows us to take any image and convert it into interactive particles is called getImageData. Whenever I see creative animation or an effect on the internet, I always inspect it. Most of them are done using libraries. How about we build our own animations completely from scratch, with no frameworks and no libraries, using just plain vanilla JavaScript, and practice fundamental programming principles and techniques in the process. Hi coders, welcome to another creative coding tutorial. Today we will build a vanilla JavaScript algorithm that can take any image of your choice. It will scan that image for pixel data and create color and brightness map that represents the image. When we have the data, we delete the image, create a very simple particle system, and we make these particles flow over the canvas at different speeds depending on the brightness of the area in the original image, recreating it as particle rainfall. This video is completely standalone and I will explain everything from scratch. I also have another tutorial where we break image into interactive particles, and another one where I explain getImageData for complete beginners. In that video I show you how to analyze image pixel by pixel, average out color values for each individual pixel, and turn image into grayscale. I will link both of these related videos down in the description. While building this effect, we will practice fundamental vanilla JavaScript principles and techniques that can be used for many other different programming projects, not just for this particular effect we are building today. We will learn about ES6 classes, array manipulation, math.random, drawImage, and getImageData built-in HTML canvas methods, and a couple of other things. I really like this animation. You can use it for your coding portfolio to impress potential employers, or just as an exercise to practice vanilla JavaScript and get yourself one step closer towards your personal front-end web development mastery. It can be used as animated background, interactive company logo, or even maybe as a loading animation. If you follow this channel and you are interested in JavaScript, HTML canvas, and creative coding, I'm sure you can come up with even more use cases and interesting variations. If this is the first time we're meeting, hi, my name is Frank and I'm a self-taught front-end web developer. I'm originally from Czech Republic, but I moved to London many years ago. Where are you from? You can leave a comment if you want. I want to know which countries my viewers are from. If you are also on a journey to become a self-taught front-end web developer, remember that you are your #1 asset. Invest in yourself and stick with it for as long as it's needed and you will be successful. Well done for watching educational content like this online, you are doing great. Keep learning, keep building projects, and don't give up. That's how you get where you want to be. In fact, let me know in the comments how long have you been studying JavaScript. It's good to stay active in online self-taught community to keep yourself motivated. We are here to help each other and learn together. I make creative coding tutorials and my goal is to help you master JavaScript step by step while having fun building visually memorable projects. Don't forget to click like if you want to see more content like this. You can also subscribe and click all notifications on the bell icon to make sure you don't miss any of my future vanilla JavaScript tutorials. This episode is not for complete JavaScript beginners. I will explain all the code today from scratch, line by line, but if this is your first JavaScript or HTML canvas project, you can check out my playlist in the video description with tutorials I specifically picked for beginners. So later, you can join me for more complex tutorials like this one. Hope you have fun, let's start coding! Let's start in index.html by creating HTML5 canvas element. I give it ID of canvas1. I also link CSS style sheet and JavaScript file here. In style CSS, I use asterisk selector to target all elements on the page, and I do global reset to make sure our styles are the same across different browsers. Margin 0, padding 0, box size and set to border box, and let's also do black background. I give canvas border 2 pixels solid white, and I center it by setting its position 50% from top. This will actually only work if I set its position to absolute. Left will also be 50%, and transform translate -50% will center it both vertically and horizontally. I make the canvas exactly the same size as the image I will be using, so for you it might be different. My image is 500 × 706 pixels. Everything else will be done with JavaScript in script.js file. I will start by bringing my image into the project, so constant variable I call for example my image, and I set it equal to new image. Now I can give it src property, which could point to an image file, but because some browsers don't like it when you analyze pixels of image with getImageData, when that image is not hosted on the same server, to avoid all different kinds of cross-origin resource sharing errors, I will convert our image into URL string. That way, the image itself is part of JavaScript file, and everything will work without errors. We can use JavaScript to convert the image, but for speed today let's use a website that will do it for us. I Google something like PNG to base64, and I choose this link. My image can be any image format, it doesn't have to be PNG. Here I can just drag and drop image I will be using. My advice is to make the image as small as possible, otherwise you will get a very long data string, and since we need to be cycling through these pixels later with JavaScript, smaller image will improve your performance. Also, if you saw the final effect, you don't need very fine image resolution for this effect to look great. So I made my image as small as possible. You can go even smaller if you are having any performance issues. I drag and drop it here, and I convert it to base64. For us to be able to use it, we need a string to start with data:image, so make sure you tick this checkbox here. Now I copy this extremely long data string, which just basically converted the entire image into a line of code, so we won't need the actual image file at all. I paste that code on line 2 to bring the image into our project. Now the usual canvas setup, const canvas equals to document.getElementById, and I pass it canvas1, the ID I gave it earlier. CTX, shortcut for context, is equal to this canvas variable, dot getContext2D. Now we have access to all 2D canvas drawing methods. I set canvas width and canvas height to be the same values I declared in style CSS to make sure the scaling is right. Now I draw the image on canvas by using built-in HTML canvas method called drawImage. It has 3 versions. We will use the middle version of this method that expects 5 arguments. The first is the image I want to draw, so my image variable from line 1. I want the image to start from top left corner of canvas, so coordinates 0, 0, and I want it to cover the entire canvas area, so end coordinates of image rectangle will be canvas width, canvas height. Sometimes drawing your image this way will not work for you, because the drawImage method only works when image has been fully loaded. To make sure we avoid any potential errors, we can wrap this whole thing in event listener. Since we gave our image src property, we can now listen for load event on it like this. And in callback function, only after the image has been fully loaded, we run all the code that depends on that image. I will just put everything inside like this, why not? We are now all set. Let's create a simple particle system that will produce a set of falling particles to flow over the image. I create a let variable called particlesArray, and I set it equal to an empty array. I use let here so that I can reassign it to a new empty array later if I want to. I create a constant variable called number of particles, and I set it to, let's say, 5000. I create a JavaScript class called particle with capital P. We will use it to create 5000 similar particle data objects, and we will push them inside particles array from line 12. Constructor is a mandatory method on JavaScript class, and it will contain blueprint for each individual particle. This .x horizontal x coordinate will be a random number between 0 and canvas width. I want particles to kind of splash over the image from top, so I set starting this .y horizontal coordinate to 0. You can also do other things here. Maybe you want the particles to flow from bottom to top or from left to right, Or maybe you want them to spiral around in a circle. You would adjust start in X and Y based on the final effect you are going for. Falling speed will be 0 at first. I will also have velocity, which will be a random number between 0 and 0.5. Basically, here I have falling speed, which will be calculated based on brightness of background. So particles will fall over black areas very fast and over light areas of the image much slower. Velocity is here just to give it some additional randomness. I think it will look good. Particles will have random size between 1 and 2.5 pixels, for example. Update method will calculate particle position for each frame before we draw it. Let's start simply by adding +1 to horizontal Y coordinate. Once particles fall below the bottom edge of canvas, I want them to reset to position 0 up top so they can fall down again. At the same time, I will also give them different random horizontal X position. This is important because particles will fall slower over light areas of the image. Actually, rather than to have all particles fall at the same speed, we can randomize it a bit. This.y plus equals this.velocity. And velocity on line 20 is a random number between 0 and 3.5. Custom draw method will simply just draw a circle to represent each particle. Begin path to start drawing. Fill style will be white. CTX arc to draw a circle. I pass it X and Y, size, start angle, and end angle. Then I call CTX fill to fill circular path with color. I create a custom function called init, shortcut for initialize. This function will just have a for loop that will run as many times depending on number of particles variable. In this case, 5000. Each time it runs, I call built-in push method on particles array from line 12. Push method places whatever we pass to it at the end of the array, so I pass it new particle. The new keyword will trigger particle class constructor on line 16. It will create one new blank particle object and assign it properties and randomized values based on the blueprint. For loop will run 5000 times, filling particle array with 5000 randomized particle objects. Now I call init to fill the array. Function animate will be our main animation loop. First, I want a semi-transparent black rectangle to be drawn over the canvas for every frame. This will give particles fading trails. I set global alpha to 0.05. This just specifies transparency value that is applied to shapes and images on canvas. 0 is fully transparent, 1 is fully opaque. Now I set fill style to RGB 000, which is black color. I draw a rectangle that covers the entire canvas. CTX fill rect, starting coordinates 0, 0, ending coordinates canvas with canvas height. I will cycle through the entire particles array, and for each particle object in the array, I call their associated update method from line 23 and a draw method we declared on line 30. This for loop will cycle through all 5000 particles for each frame of animation. It will recalculate their position with update method, and it will draw them at their new coordinates with draw method. Now I just call animate to kick off animation loop. This will not work because I also have to call a request animation frame here and I pass it animate. Request animation frame is a built-in JavaScript method. When I pass it animate, the name of its parent function from line 43, that way animate will run all its code and it will just call itself again here on line 51, create an animation loop through a programming principle called recursion, when function calls itself over and over. That worked. Now we have falling white particles that leave trails. Perfect. I can temporarily copy draw image call from line 10 and I put it inside animation loop so that we can see the original image for now. Click the like please if you're getting any value from this tutorial. You can also subscribe and hit all notifications to make sure you don't miss any of my future creative coding vanilla JavaScript tutorials. Particles are falling and ignoring the image. How do I make them fall at different speeds based on brightness of the area they are moving over? One way to do that is to create a brightness map of the entire image. It will correspond to X and Y coordinates of each pixel. Then I can run this information against particle's current x and y position and adjust particle's speed based on its current coordinates. Let's do it step by step. First, I create a new let variable called mappedImage. This will be an empty array at first. My goal is to have this array hold brightness value of each pixel in the image along with that pixel's x and y coordinates, so I can compare it to x and y coordinates of each particle and adjust their movement speed accordingly. So on the first page load, we just draw image on canvas here on line 10. I create a custom variable called, for example, pixels, and I set it equal to ctx.getImageData built-in canvas method. This method scans area of canvas for pixel information, and it will return an array-like object that holds red, green, blue, and alpha value for each individual pixel in the scanned area. I want to scan the entire canvas, so I pass it 0, 0 as starting coordinates and canvas width, canvas height as the end coordinates. So now my custom pixels variable holds whatever getImageData returned after scanning the designated area, in our case the entire canvas. If I console log pixels, I see this returned image data object. If I open it, it contains an array called data. It also contains height and width attributes that correspond to width and height of the scanned area. We scanned the entire canvas, so width and height correspond to canvas width and canvas height from lines 7 and 8. Let's inspect the data array. You can see it is called UINT clamped array, that means unassigned integer, so it can only contain elements that are whole numbers with no decimal points. It also says clamped, because these numbers are limited to a range between 0 and 255. If you worked with CSS before, you know that in RGBA color declaration, every color can be declared by a combination of red, green, and blue, with values between 0 and 255 for each. We established that each element in this data array could only be a number between 0 and 255. If you look at the data structure, you can see that every 4 pixels in the array combined create RGBA color declaration of 1 pixel in our image. So this one, for example, is 0 for red, 0 for green, 0 for blue, and 255 for alpha opacity. In this case, alpha is also declared as a value between 0, which is fully transparent, to 255, fully opaque. We can double check if we are right about this. We have an array of 1,412,000 elements, and we know that each 4 elements in this array represent RGBA color value of 1 pixel. So 1,412,000 divided by 4 is 353,000. These numbers depend on the size of the image you uploaded, so for you it might be different. We know the image I'm using is 500 pixels wide and 706 pixels high. So 500 times 706 is also 353,000, so that checks out. Let's look at the pixels with color that are not black. For example, here we have 111 for red, 83 for green, blue, and 255 for alpha. Then 139 is red of the next pixel, and so on. So now we understand how the color data returned by getImageData method is organized. We can cycle through it and save it in our own array, and since we know width and height of the scanned area, we can calculate x and y coordinates of each pixel. Since we know how many pixels fit on one row, and we know how many rows and how many columns our image has. This is the only a bit more difficult part in this tutorial, so if you are a beginner, keep in mind this is not easy. Don't feel bad if you struggle to imagine what exactly is going on. I made a beginner-friendly version of this technique where we cycle through all pixels and turn image into grayscale. Sometimes it's easier to first try this with a simple project. I will link it in the video description. We will cycle through every pixel in this image, row by row, from left to right, starting from the top left corner. So the first for loop will have a vertical y coordinate at 0. Our image is 500 pixels wide, so y will be 0 and x will be 0, 1, 2, 3, all the way to 500. Then we increase y to 1, and again we cycle through pixels 0 to 500 horizontally. Then we increase y to 2, and we cycle through the entire x coordinate of pixels again. We will do this 706 times because our image is 706 pixels high, which means it contains 706 rows of horizontal pixels. The code will look like this. We will use nested for loops, which means loop inside of another loop. The outer loop will represent vertical y-coordinate, so it will run 706 times, because our image is 706 pixels high, which means we have 706 rows of pixels. We will start with top row 0 and go all the way down to row 706 on the bottom. For each row of pixels in the image, I will create an array called row. It will hold our pixel data for each of the rows. For every one of these rows, we enter the inner loop, and index of this inner loop will correspond to horizontal x-coordinate of pixel within the image, starting from x-coordinate 0 and going to the right until we reach pixel 500, because our image is 500 pixels wide. Then we just exit the inner loop, increase y by 1, therefore jump in to the next row and go in through the horizontal pixels from left to right, from 0 to 500 again. I'm not sure if I'm over-explaining this or if you need me to explain it more. Let me know in the comments, please. I'm just trying to make it accessible for beginners as well. So now we have two nested for loops that work together to cycle through every single pixel in the image. For each individual pixel, I want to read its color values, so here I will create a temporary variables for red, green, and blue. Red for each pixel will be pixels variable from line 11, dot data, which is this data object here with 1,412,000 elements, where we know each 4 elements represent red, green, blue, and alpha of 1 pixel. There are many ways we can skip array index by 4. I will use this formula. I'm sure there is easier way to do this. Let me know in the comments. The first part that says y times 4 times pixels width just keeps track of overall number of array elements from previous rows. And the second part that says x times 4 just adds the items from the current row to it. So the final number we get is array position of red value for pixel with this y-coordinate and this x-coordinate. This is not programming anymore, this is more like advanced logic and visualization. I wish I had more visual tools to show you better what's going on. I will try to come up with something for future tutorials. In the meantime, let's just finish this. Once we know what index red color value is, it's easy to get green, blue, and alpha because we know that this data array is organized in a way where red is followed by green, which is followed by blue, and alpha. Since I know this, I know that green is whatever red is plus 1. And blue is position of red in pixels array plus 2. So now I have calculated red, green, and blue of pixels at this vertical y-coordinate and this horizontal x-coordinate. I could just add them together and divide them by 3 to get their average value, which is the same technique we used to turn image into grayscale in the previous episode for beginners, link in the video description. There is a strange thing about human eye that we don't perceive red, green, and blue the same. The same amount of red is not the same brightness as the same amount of blue when perceived by human eye. We can create a simple utility function that will take red, green, and blue value we just calculated for each pixel. It will adjust them by different amount based on human brightness perception, and it will return a single number representing relative brightness of that pixel. Custom function called, for example, calculate relative brightness. It will expect 3 arguments, red, green, and blue. We calculated on lines 20, 21, and 22. It will just straight up return a number calculated by following formula. I found this formula online. We don't have to fully understand it because all it does, it adjusts red, green, and blue by different amounts to make up for the fact that the human eye doesn't perceive these 3 colors the same when it comes to their relative brightness. This is just for fun to make it more visually accurate, I guess. As I said, this formula could have been a simple add red plus green plus blue divided by 3 to get average, and it would work as well. Of course, then you have to adjust the rest of the code like particle falling speed based on the range of numbers this would return. Up on line 23, I create a variable called brightness. Thanks to JavaScript principle called hoisting, I can call my custom calculate relative brightness function I declared on line 27 up here on line 23 before that function is declared. Hoisting allows us to do that. It expects 3 arguments, so I pass it red. I calculated here on line 20. This simply is a reference to index in pixels array as we cycle through it. So for example, for this pixel, red would be 0, green would be 0, and blue would be 0. So brightness is 0 as well. I create a constant variable called cell and I set it equal to an array. I give it property called cell brightness and I set it equal to brightness variable from line 23. Here inside the cell array, you could also create another property called cell color and create RGB color declaration, where you concatenate red, green, and blue, and you save this pixel's actual color. So we can use it in fill style on draw method for that particle. That way you can persist original colors of the image. More on that later. So we calculated relative brightness of pixel of this vertical Y and this horizontal X coordinate and saved it in a custom array I call cell. I take row variable from line 18 and I push cell from line 24 to that array. We will create this cell array for every pixel in every row, so row variable from line 18 will be created 706 times because outside for loop will run for every row of our image, which is 706 pixels high. And inside of each of these 706 rows, we create cell array here on line 24. We will have 500 cells for each row because our image is 500 pixels wide. Each cell holds relative brightness value for each individual pixel in the image. So every time the loop is done and we pushed 500 cells into that row, we take the entire row from line 18 and push it into mapped image array from line 16. That way, when all these loops have run, we have mapped image array with 706 row arrays. Inside of each of these row arrays, there are 500 cell arrays. Each cell array from line 24 represents one pixel in the image. We did it! We cycled through pixels variable from line 11, we took that image data and created our own array called mapped image that contains brightness values for each pixel on canvas. If I console log mapped image, you see 706 items. These are the row arrays from line 18. Each one holds 500 cell elements from line 24, and each cell is an array that contains only one element. That is this cell brightness property that contains relative brightness of each pixel we calculated. We will get a lot of zeros as cell brightness value because there are large black areas around my image. But if I keep looking, I will be able to find other values here as well. See? Now I just need to take this information about brightness I stored in mapped image variable and somehow make particles fall at different speeds based on that. First of all, we need to navigate in indexes of that array based on particles' current x and y coordinates. Since array index has to be integer, whole number with no decimal points, here on line 48 and 49 inside particles class constructor, I create position 1 and position 2 custom variables that will simply round down this.x and this.y, making sure that these numbers don't have decimal points. I also need to put these values here inside update method to make sure every time we update x and y position, these values stay rounded down as whole numbers, as integers. Now the main trick of how this entire effect works. I will adjust this.speed from line 45. I will literally take values from my custom mapped image array, and since we organized pixel data in the array to the same width and height as our canvas using our nested for loops, I pull value from a mapped image array based on particles' current x and y position. This .position1 corresponds to particles' current vertical y coordinate as we declared on line 52, and adding it as index like this on line 54 will access custom row array in mapped image which has the same vertical y position as the particle currently has. Then we go one level deeper inside map image array to access horizontal x position. I called these arrays cells, if you remember, and they contain only one property called cell brightness, so that's array position 0. So what we have here is mapped image, custom row array from line 18, custom cell array from line 24, and it has only one element I called cell brightness from line 25, so position in this array is 0. And since outer loop that created mapped image on line 17 matches height of canvas and inner loop from line 19 matches canvas width, the brightness information held in mapped image will correspond exactly with our image. Let me show you. I appreciate this might be hard to follow and imagine what's going on at first. If you can follow what I'm explaining here with no problems, congratulations, you are not in majority of us. It took me a while to realize how this works to create a full mental picture. I bet some of you will be able to tell me there is a much simpler way to do this, and I am looking forward to these comments. I've learned a lot from your comments already, so please keep them coming. So here on line 54, I take speed from line 45, and I assign it to brightness value of that area in the original image. Then I create a custom variable, let's call it movement for example. Relative brightness we calculated earlier and which is now reflected in this.speed because of line 54 is a small number between 0 and 2.5 approximately, I think. Since I want dark particles that have brightness close to 0 move very fast, and I want light particles with relative brightness close to 2.5 to move very slow, I flip it by saying 2.5, which is the maximum, minus this.speed. And I also want to randomize it a bit, so if we have a large area of particles with the same color, they still don't move exactly the same speed. To do that, I just do plus this.velocity from line 46. Now, here on line 57, I say this.y plus equals movement, and we should be able to see that particles react to image now. Velocity on line 46 is too high. Let's change it to a random number between 0 and 0.5. Perfect. Important part of this effect is that the faster the particles move, the more transparent they are. On line 77 inside animate, I remove the image so it's not being redrawn over and over. You can see we are getting something nice on canvas already. Code between lines 77 and 79 just creates a semi-transparent rectangle that is being drawn on canvas over and over, given particles fade in trails. Once we draw it, I want global alpha to increase to, let's say, 0.2. And here, inside for loop that cycles through all particles for every animation frame, before we actually draw the particle, I will adjust global alpha for that particle to be equal to particle's speed property. That's a bit too much. Let's half it, speed times 0.5. Up on line 10 on the first page load, I draw the original image on canvas using built-in HTML canvas drawImage method. On line 11, I call getImageData on it to get information about all its pixels, and I save it to my custom pixels variable. At that point, I don't need the image anymore, so I just clear canvas, deleting the original image. When I do this, we will never see that image at all. It will be drawn, analyzed, and deleted when page loads very fast. There are a lot of moving parts and many ways to customize this effect. You can try to tweak some values and see what it does. Idea for this effect came from this brilliant CodePen, link in the video description. Luis also has many other interesting animations on there. You can follow him if you want. There is a lot of code in that CodePen. Today we wrote our own version, line by line, using just plain vanilla JavaScript, and we explained exactly what's going on each line of code. I hope it gave you some value and brought you one step closer to becoming a master of web animation. Now you should be able to understand it and tweak it to make your own variations, or maybe even build on it and create something completely new. Are you able to take what we learned today and use pixel array to keep track of colors of the original image and make particles change colors based on that? It should look something like this. I had so much fun today, hope you learned something new, click the like if you did. If you want more creative coding with vanilla JavaScript, check out some of my playlists, I will see you there.